Hi there. In a recent video on a power supply I bought and fixed, I complained that it was missing the shorting links connecting the sense inputs to the outputs. These links are needed when you don't want to use 4-wire mode, where the power supply compensates for any voltage drop on the connecting wires to your load. Proper shorting links are hard to find and disproportionately expensive for what they are. Basically a metal plate with cutouts so they can slide over binding posts spaced 3/4 of an inch or about 1.9 centimeters apart. The commercial ones are usually made from nickel-plated brass for corrosion resistance. In that video I said I may make my own shorting links, and if I do, I will make a video about it, which is the one you are now watching. Starting with the brass, here's a strip of 1.2 mm thick brass, 20 mm wide and 200 mm long. I bought it online for £6.59 delivered, which is about $9. The sheet is covered in foil to protect it. I have to admit I'm not very good at mechanical stuff, so I designed a drill template on my computer. My idea was to create at least 2 rows of 6 shorting links. I show only circles representing 6.5 mm drill holes for the first 2. You have to imagine the others. Also, of course, the holes have to be cut open on one side to be able to slide over the binding posts. I glued the drill template on the foil of one side of the brass strip. The foil prevents the glue from messing up the brass, but it sticks well enough for the drilling. As expected, this work was not going too well. I would also say, when I do this again, a width of 1 cm per link is too little. It makes the bridge over the hole rather thin, increases the electrical resistance and weakens it mechanically. Indeed, I only managed to get 10 halfway usable ones instead of 12. You may also note a small 2 mm hole in each. My idea was to use that hole to run a wire through it when it comes to nickel plating. This avoids the problem of having to move the alligator clips halfway so that the surface under the alligator clip is coated as well. Since the brass was protected by foil, I only have to get rid of my fingerprints, and for that a bath in acetone will do. After a while I took them out, rinsed them with clean water and dried them, all without touching them. For the plating process, I followed what everyone on the internet seems to do, although specifics like quantities and concentrations are very vague. Apparently it doesn't seem to matter too much. First, I need to create a plating solution which consists of dissolved nickel acetate. I started with 20% acetic acid or really strong vinegar, which I had handy. I added 200 milliliters of it into a beaker. To this I added 200 milliliters of water, into which I had first dissolved a pinch of salt to improve the conductivity of the liquid. You don't want to use more because salt will break down into sodium and chlorine during the process, and chlorine isn't too healthy. The electrodes are pure nickel rods, 100 millimeters long and 6 millimeters diameter. I bought for this purpose. That turned out to be quite expensive. 16 pounds for both, or $22, but they can be used many more times. I used my bench power supply at about 12 volts, and as soon as I turned it on, bubbles started to form on the electrodes. Lots more on the negative one, which is the one on the left, than on the positive one on the right. The current was just shy of 150 milliamps. The negative electrode has lots of bubbles, which consists of hydrogen. The positive electrode has far fewer bubbles, mostly oxygen. The goal is to dissolve nickel from the positive electrode into the solution to form nickel acetate, which should turn the solution green. This may take hours, certainly at this speed. A bit impatiently, I increased the voltage to 20 volts, which causes 285 milliamps or so. That means 5.7 watts are going into the solution. And there is definitely more action. And I fancy the first hint of the solution turning green. I left it bubbling along to do something else. Returning after slightly more than 1 hour, and I noticed that the current had increased quite a bit. In fact, it increased slowly while I was watching. 9.7 watts are going into the solution now. Yes, definitely turning green. And if you look at the bottom end of the positive electrode on the right closely, there are streaks of something dissolving. That will be nickel. Another hour and the color has intensified and the solution has heated up. About 47 degrees Celsius or 116 degrees Fahrenheit. No wonder with all that energy going in. About 10 minutes later I did another check of the temperature and it has increased rapidly. 55 degrees, 56 degrees or 133 degrees Fahrenheit, and it's climbing steadily. And the current has risen to more than 1.1 amps, 22 watts. I let this run a bit so you can see the current climbing in real time. I think I will call the preparation of the solution done now. After turning the power off, I disconnected the negative electrode. The negative lead now goes to this blue wire, which I will use to hang one of the shorting links into the solution. For my very first nickel plating attempt, I picked one of the failed pieces. But it turns out that the wire is too big or the hole in the shorting link is too small, whichever way you prefer, and switch to a much thinner wire with brown insulation this time. It fits to the hole, but staying there is a different matter. Finally, into the solution, trying very hard not to cause short circuits by touching the anode with it. The voltage is set to just 1.5 volts because plating should be done at low currents for a fine and even coating. I leave it in for a minute and then rinse it in clear water. It is nicely coated, but it's quite tricky to see the difference between shiny brass and shiny nickel. Maybe I should leave the pieces in for a bit longer. So onwards to the first real piece. I attach it to the wire, taking care not to touch it. In it goes. The current is already on. For all subsequent pieces I had the current off, which avoids the danger of touching the electrode with a springy wire. Only after it was positioned correctly I turned the power on and started the timer, set to 5 minutes. At 1.5 volts the current is just 35 milliamps. After the timer beeps, it's into the rinse bath and then onto the paper towel for drying. Here's one of the subsequent pieces. Seconds after the power is turned on, bubbles start to form. I hope hear the difference in color between the golden hue of an untreated piece on the left and the more silvery color of a freshly nickel-plated one on the right is more visible. After I was finished, I took the electrodes out and examined them. The upper one is the positive one and it's very pitted because it provided the nickel into the solution and of course onto my shorting links. While making the solution, the negative electrode actually also absorbs nickel. There are nickel dots all over its surface, but most interesting, a whole nest of nickel whiskers at the very end. They are surprisingly hard and stable. I suspect that along the rod, the turbulent stream of hydrogen bubbles prevented anything more than depositing tiny nickel dots, but on the very end bit of the rod there was far less bubble action and so the whiskers could grow larger and larger. The solution can be reused for more nickel plating in the future, saving lots of time of course. So I pour the beaker content into a suitable bottle. Here are my DIY nickel-plated shorting links. Sure, they are pretty ugly, but I learned a lot and the next batch will be better. But the bar is quite high because just look at these beauties. Kindly donated to the channel by Johannes from his company Wrytech in Germany after seeing my video on the power supply. Johannes did not ask to be mentioned or that the links are even shown, but I think they deserve to be shown. I leave a link to his company in the description of the video. I'm curious how much resistance my self-made ones have. These kind of tests are a bit ambiguous because it is impossible to put the Kelvin probes exactly to the same spot every time. Okay, with that in mind, it's about 0.65 milliohms, which is certainly very small. The gold-plated Wrytech links beat that by being 0 ohms. That is below what this meter can measure. gold-plated double-sided PCBs as shorting links is a great idea, but I was wondering if they would be even better if the two sides would be connected using wires. You see, if I measure, there's no continuity between the front and the rear. I asked Johannes about that and he told me not using vias was a conscious decision based on examples of shorting links from Fluke that also have none, possibly to reduce thermal gradients and therefore thermal voltages. Proper binding posts will connect to both sides anyway. Hang on, proper binding posts sure, but the Kelvin probes I just used for measuring resistance won't. Was the 0 ohm I measured for the Wrytech links even real? I set up a test using two 1K resistors I had handy to represent the two surfaces. 1K is of course ridiculously high, but it will show the effect. The resistors are just held in parallel by the two terminal posts. They are not connected. Simulating the measurement I did earlier, and what do you know? 0 ohm. Does it matter which way around the probes are? Yes, with the black one reversed we now have 42 ohms, not 500 as you would expect. So in either case it's a wrong result, which clearly shows one of the pitfalls of Kelvin probes during 4-wire resistance measurements. Resistance measurement drives a known current through a resistor and measures the voltage over it. From both values the resistance can be calculated. In 2-wire mode, the resistance of the measurement leads is included. 4-wire modes avoids this. 2 wires send the current through the resistor. 2 further wires are used to measure the voltage drop directly at the same location where the current is injected. There's hardly any current flowing in the voltage wires, so the wire resistance doesn't matter. For convenience, the connection to the object is often done using Kelvin probes. I simplify their jaws with little triangles here. When probing the Wrytech links this way, the current flows through the lower surface and the voltage is checked across the unconnected upper surface. 0 voltage drop means 0 resistance. If you reverse one of the Kelvin probes, the current cannot flow properly because it has only a high impedance voltage sensor to go to, and similar the voltage probe connects to a current sink. No wonder the results are weird. I think the only way to get valid results is to actually measure the Wrytech shorting links resistance when inside proper binding posts with both sides connected. Let's see what we get. About 1.44 milliohm. Of course, that includes now the resistance of the binding post as well. Replacing the Wrytech links with one of my production, and it's 1.34 milliohms, slightly less, but in the same ballpark. Okay, these are the results with binding posts that have two metal surfaces. This binding post and several other similar types have metal discs only on one side. If I put one of Wrytech's shorting links in, it is connected on the rear but not on the front. In other words, the resistance represented by this link has doubled. One would think the fact that the shorting link rides on the metal of the binding post shaft would connect both sides, but this link is essentially a PCB, and the inside of the PCB and hence the edge is fiberglass based and non-conducting. This other binding post also connects to one side. Unless you use the shorting links for conducting massive amount of current, that should cause no issues. Of course, my nickel-plated beauties don't have this problem. They are solid metal. As long as one side has connection to the binding post, both sides, in fact the whole body, conducts. The proper binding posts on my power supplies use both sides. Anyway, the current between sense and output is tiny, so even if they did not, it really would not matter. To sum up, making your own nickel-plated shorting links is totally possible, but only becomes economical if you need lots of them and your time fabricating them doesn't count. For small numbers, Wrytech links provide another alternative to those I already mentioned in the power supply video. A big thanks to Johannes for sending them in. If you like my videos, don't forget to like and subscribe and help growing this channel, and consider becoming a Patreon. The link's in the description. Thanks for watching.